Dear Professor Musen, my heartfelt congratulations on receiving the honorary doctorate from the University of Fribourg. You come from afar, from Stanford University in California, actually. What associations do you have with Switzerland, or more precisely with our university, the University of Fribourg?
I have a lot of associations in that 15 years ago, Hans-Georg Film, one of your faculty members, discovered our lab at Stanford and from time to time has come and visited us. We've come to his place to visit him, and so there's been a lot of exchange going on, which has been very good. I've had a lot of work with the World Health Organization, so that brings me to Geneva a lot. And Switzerland is just a nice place to be.
Thank you. Let's talk a bit about your work. As a professor of biomedical informatics and director of Stanford Center of Biomedical Informatics Research, you are globally renowned for initiating and contributing to the development of a so-called open source software called Protégé for managing and creating ontologies. Please allow me to ask the simple question, what are ontologies?
What are ontologies? Well, ontologies go back to the Greek philosophers who tried to understand their world and tried to identify what are the components of existence, what are the ways in which those components relate to one another. And that sounds very philosophical and very arcane, but in the everyday world, all the time, we're looking at things in the world and trying to classify them, to see how they relate to one another. When we go to a restaurant, we try to figure out, gee, what are the fish dishes that we might want to have? What are the meat dishes we might want to have? Of the meat dishes, what are the different kinds of meat that the restaurant serves? And everything we do in life requires us to deal with classification. Well, in everyday life, we're always classifying, and in science, which is where most of my work takes place, we're trying to understand what are the things that scientists care about and how can we understand them in terms of classification systems so that if we understand something somewhere in the classification system, we can make inferences about how it relates to everything else in the classification.
Okay, and what does Protégé, this technology, do exactly? What is its purpose?
Mainly as an editor. It doesn't create a classification de novo. It allows someone who wants to articulate what's the best way to structure the ways in which things are classified, to do so in a visual way and to see exactly how things are related to one another and to make sure that those relationships hold so that that structure, which then gets turned into a data structure, can be used by computers to reason about how things are related to one another. So ultimately, Protégé allows you to articulate what are the kinds of bones in the body, how are those bones related to one another, and ultimately then a computer can look at that ontology and say, oh, the hip bone's connected to the leg bone, and make those kinds of inferences.
So it could be an instrument, for example, for doctors, could be helpful for doctors in medicine.
It could be used directly by doctors. It's really designed to be used by computers, and then in turn might be used by doctors. Exactly. The goal is to structure the information so that a computer can reason about it, so that a doctor can ask the right kinds of questions and get reasonable answers back.
Exactly. This Protégé, this software, is a so-called symbolic AI, artificial intelligence, in contrast to, for example, large language models, which are referred to as sub-symbolic AIs. And sooner or later, the goal is to connect these two systems. How can university research contribute to this?
Well, these two kinds of AI systems do very different things. I think most of us over the past year have become really enchanted by the amazing capabilities of sub-symbolic AI. LLMs do amazing things. They can tell us all kinds of answers to very, very difficult questions. The problem is that these sub-symbolic AI systems don't know anything. They know how to look at the kinds of responses to questions that other people have recorded online or in other kinds of textual sources. They know how to compose those together to give an answer, but they don't know what the answer means. And I think what's very interesting from my perspective is that if we can combine that kind of really exciting, efficient reasoning with reasoning that actually can understand the relationship between the symbols in the world that we want to reason about, we have the best of both situations. But I think on their own, some symbolic AI systems are not going to be able to do very complicated things. They're not going to solve equations. They're not going to do algebra. They're not going to do your kids' arithmetic homework, at least very well. And what we can do with symbolic AI is reason about things as complicated as clinical medicine and add to that the kinds of capabilities that large language models bring.
The work of a professor for biomedical informatics, not least, bridges the gap between biomedical sciences and informatics. Why is that so important, to bridge this gap?
Well, a lot of people would say that biology is obviously a complicated science, but fundamentally it's an information science. For us to understand biology, we have to understand how information gets transmitted through the cell. How does information encoded in DNA get translated into proteins? How do those protein structures bring about the functions of the cell? That's all information theory, but in a way. And I think there's a lot that informatics can offer in helping us to understand how that all fits together. When it comes to clinical medicine, a lot of what doctors do is the need to be able to look at a patient's situation, to understand what are the complexities of that situation, to be able to use the biomedical literature to make the best judgment about what is the right thing to do in that particular setting. That's information science. And so even though we think about information science perhaps in a rather abstract way, when it comes to biology and medicine, we're solving very real-world problems that have real implications for people, and we need to understand how information in that setting can actually lead us to the right answers that we need.
Before we come to the end of our little conversation, let me ask you one last question. What is your next big challenge, apart maybe from eating a fondue in Switzerland?
Well, still working on that one. With respect to the work we're doing in my laboratory, we've been taking the work that we started with Protégé 30 years ago and using ontologies in ways which help us solve increasingly interesting problems in biomedicine. Right now, the problem we're trying to solve is how can we look at the data that scientists create in biomedicine that get stored in online data sets and use those data sets to make new discoveries. And that really requires us to understand what were the situations under which experiments were made, what were the original investigators thinking when they did their experiments. We capture all of that as terms and ontologies. And we reason about those terms to understand what was done, what was the nature of the experiment, how does this experiment perhaps relate to other experiments. And so for me, the real excitement is being able to reason about scientific results in hopes that those results will lead us to new discoveries that we haven't made yet.
Thank you very much, Professor Musen, for this conversation. I wish you a very nice day in Switzerland.
Thank you so much.